Hello students, welcome to lecture number 4 of computer architecture course. Today what we are going to look at is introduction to instructions, and by the word instructions we basically mean how the computer perceives instructions to convert that to a series of binary numbers that it can execute through hardware. So now we are ready to explain the difference between the way humans instruct computers and the way computers sees instruction. Okay, so instructions are usually kept in the computer as a series of high and low electronic signals and may be represented as numbers. In fact, each piece of an instruction can be considered as an individual number, and placing these numbers side by side forms an instruction. Okay. You had already seen in the previous lecture about how the performance analysis of processors work, and you already know the basics of how MIPS processor is usually judged in terms of its efficacy, in terms of MIPS rating, clock cycles, and so on. So now is a good time to see how we can use those performance metrics to enhance the performance of a computer using instructions. So let us first have a look at the categories of instruction. So the first type is an arithmetic type. It can be further classified into integer and floating point. The second is memory access instruction type, which usually comprises of instructions which are load stored based. The third is control flow type, which comprises of three types of instructions, which is jump based, conditional branching, call and return. So when I'm referring to instructions type which are arithmetic based, we could have two type of arithmetic computers. One is integer based, second is floating point based. So instructions of that could vary accordingly. Floating points we will again talk in details in some upcoming lectures, because there are dedicated lectures for floating point representations as per IEEE 754 standards. We will talk about that in specific lectures related to floating point numbers only, or floating point arithmetics. Memory access instruction types are those instructions which usually have memory involvement when we want to transfer data between memory to register or register to memory, so on and so forth. And control flow is usually conditional decision based instructions, where the decision could be unconditional or it could be conditional. Okay, so they have usually a prefixed condition based on which a decision is taken. So we'll look into all these type of instructions in today's lecture. Now before we jump into knowing what the type of instructions are usually used in MIPS, it's important to understand that we are actually talking about 32-bit MIPS processor in this course. So we are referring to the computer architecture, that is 32-bit MIPS processor, and everything it operates upon is on registers. And coincidentally we also have 32 registers in 32-bit MIPS processors. So these 32 registers could be as follows. We have a 0 register whose register number is 0. The usage is for constant 0. We have registers $V0 to $V1 whose register numbers are 2 to 3, and they are usually used for returning values. Then we have register names as $A0 to $A3. Register numbers are 4 to 7, and they usually used for arguments. $T0 to $T7 register numbers are 8 to 15, and they usually used for temporary storage. $S0 to $S7, which is register number 16 to 23, and they are usually used for storing saved values. $T8 to $T9, these correspond to register numbers 24 and 25. They are again used for temporary purposes. And then we have $GP, which is register number 28, which is used for global pointer. $SP, register number is 29, used for stack pointer. $FP, register number is 30, used for frame pointer. $RA, register number is 31 used for return address. So as you could see that we have a wide variety of instructions, registers, based on which instructions will be used and converted to respective assembly language code. As I pointed out here in the green box, $GP to $RA is not that frequently used, although $RA you will find usage in many places, but it's still not that frequently used as the above registers from $0 to $T9. They are very frequently used, and $RA is one of those registers which actually play a role in the conditional type instructions. Okay, when we want to return back to a particular address, it plays a very important role. Okay, we'll do examples so you will understand it better to see how it actually works. So since registers are usually referred to by almost all instructions, there must be a convention to map register names into numbers. So that's the reason we have this table here. So in MIPS assembly language, registers S0 to S7 map to register 16 to 23, as you could see. So that actually means $S0 is register 16, $S1 is register 17, $S2 is register 18, and so on. And $T0 means register 8, $T1 means register 9, and so on. So that's how basically the mapping convention of the register names to register numbers work in MIPS 32-bit processor. Now let us have a look at how to translate a MIPS assembly instruction into its respective machine instruction. But before we do that, let me first also give you some idea about how a high-level code gets converted to its equivalent MIPS code, MIPS code. Okay. Most instructions have 3 operands, as you could see, and operand order is also fixed. So you have a destination followed by source 1 followed by source 2. So example, if the piece of code is z equals to y plus x, then the MIPS code will be add, because we are adding $S0, comma $S1, comma $S2. This could be one of the possible codes. $S1 corresponds to y, $S2 corresponds to x, and they are summed up and stored in $S0. Mind it, all the 3 are registers, and these 3 register names $S0, $S1, $S2 are associated with variables by the compiler. The compiler can choose any register to associate it as per its usage policy. Okay. Let's look into another high level code. So you have x equals to p plus q plus r and z equals to y minus x. So the equivalent MIPS code will be add $T0, comma $S1, comma $S2. So what we are doing, we are basically adding S1 and S2, that is q plus r, and storing onto a temporary register, which is $T0. Once we store that to a temporary register, it is again added with another register value, which is $S3, which is the equivalent register for p, and then once it is added, it is again stored back to $S0 into a saved register, right? So $S0 now has the content of x, because we have already added $T0 with $S3. In the next line sub, we are actually subtracting $S0 from $S5. $S0 is corresponding to x, $S5 is corresponding to y. So once it is subtracted, we have a result $S4 where it is stored. So $S4 corresponds to z. So in 3 MIPS instructions, we are able to execute a 2-line high level code, as you could see. So operands must be registers, as you can see, and MIPS provides 32 registers for this purpose. So you could see from the previous example and the current example that arithmetic operations could be performed in the way how I've done using examples or instructions of add and sub. Now let's move into a little bit more details of how to convert or translate a MIPS assembly instruction into machine instruction or machine code. Because as I said, if you recall, I said at the beginning that instructions are kept in the computer as a series of high and low electronic signals and may be represented as numbers. In fact, each piece of an instruction can be considered as an individual number, and placing these numbers side by side will form the instruction. Okay, so let us first classify the different types of MIPS instruction into categories. So first we have an arithmetic, logic, shift and comparison type. Then we have control instructions, which could be branch and jump. We'll talk about this later. Then we have a load and store. Then we have others, okay, such as exception register, movement to and from GP registers and so on. Now we also have three instruction encoding formats that we actually use to translate a MIPS assembly instruction into a machine instruction. So the first is R type. We have a 6-bit opcode, 5-bit RS, 5-bit RT, 5-bit RD, 5-bit shamt and 6-bit function code. So RS, RT, RD, they are actually the sources and the destination register. RS, RT are the sources and RD is the destination. Shamt is a shift amount in case we have an instruction where we need to do some shifting. And 6-bit function opcode or function code is actually one of the variations to represent what type of R-type instruction we are using in that particular instance. The next type is I-type. I-type has 6-bit opcode, 5-bit RS, 5-bit RT and 16-bit immediate field. Now RS here is the source register, RT is the destination register and 16-bit immediate is the 16-bit address or offset. We'll do an example so you'll understand it better. So just for now, keep in mind that we do not have 5-bit shamt 6-bit function code in case of I-type. We only have opcode, RS, RT and immediate field. 4 different types here. And the third type is J-type. J-type has a 6-bit opcode and a 26-bit pseudo direct address. So we'll put a pseudo direct address in case of that 26-bit field that we have. So it's address field and an opcode field that we have here. And that is again quite different from I-type and R-type. Now let us have a look at the layout of the instruction. The 32-bit layout of the instruction. The 32-bit layout of the MIPS instruction format for R-type is as follows. You have an opcode at 31 to 26, RS at 25 to 21 and RT at 20, 16, RD from 11 to 15, shamt from 6 to 10 and function from 5 down to 0. So that makes up 32-bit. Similarly for I-type, you have opcode from 31 down to 26, RS at 25 down to 21, RT at 20 down to 16 and immediate field from 15 down to 0. So that makes it up for 16-bit immediate field that we were talking about in the previous slide. And for the J-type, we have 31 down to 26, which is the 6-bit opcode, and 25 down to 0, which is the pseudo direct jump address that we are referring to. Okay, so as you could see that the MIPS instruction takes exactly 32 bits. Now once we convert that to its numeric version, we will find out that it is actually representing the machine language or the machine code of the respective instruction. So let's see. Okay, let's do an example to understand it better. So example, you have an instruction add $T0, $S1, $S2, where the registers have been associated by the compilers, and $T0 stands for 9, $S1 stands for register 17, $S2 stands for register 18. So if you want to put this instruction as per the R-type layout of the instruction encoding format, what will it be looking like? So RS, as I said, stands for the identifier of the first source register. RT stands for the identifier of the second source register. So in this case, the first source register will be 17, second source register will be 18. And RD, which is the identifier of the destination register, that will stand for register number 9. Shift amount in this case is going to be 0 because you do not have any shift amount. And the function code, okay, which actually represents the opcode variant, is going to be 35, because 35 is the number that actually represents my mistake, not 35, it's going to be 32 for add and 34 for subtract, okay, and the opcode for the R type will be 0. So the opcode value will be 0 for R type, and the variation, whether it's an add or a sub, will have a different number, and that will be 32 or 34, either of the two, depending on whether it's an add or a sub. Okay. So as you could see, although multiple formats actually complicate the hardware, because we eventually want everything to be converted and processed through the hardware, we can reduce the complexity by keeping the formats similar. That is why we have the first three fields of the R type, I type as the same size and have the pretty much the similar names. The length of the 4 type in I type is equal to the sum of the lengths of the last 3 fields of the R type. Okay, so that's why we want to keep a certain similarity between all the 3 formats. So what I said that basically for the R type instruction, the opcode is going to have a value of 0, and the function type value, the last 6 bit, is going to have a value of 32 or 34 depending on whether you do add or a sub. Okay, now let's move to the next type, which is I type. So you see an example, we have LW $T0, 52, and in the bracket we have $S3. Now what does this signify? Let me first explain that. So you have a source register which is $S3, that is storing the base address, okay, of the memory. 52 is the offset, that is the value of the immediate field, that will be added with the content of register S3, and whatever number you get from that location in memory, the value will be loaded onto register $T0. So here T0 is register number 8 and $S3 is register number 19. Okay, so if you do that, so automatically as per the template you see that 19 becomes the source register value and 8 becomes the destination register value. That's what I'm trying to say here basically. Okay, so RS is basically the source register and RT is the destination register. If you see the I type format, that's how it is. So here RS is 19 and RT is 8. So we are adding the content of S3 with the offset 52, and whatever value you get, computed value that you get, that will act as the memory location from where the content of that location will be loaded onto register T0, because S3 is storing the address of the base address of the memory, and 52 is the offset that will be added to that. So if you put into the I type format, you basically have 35, which stands for the opcode of LW, and then you have 19, which is the source register, which is RS, then you have RT, which is the destination register, and then you have the constant, which is the immediate field, which is the value 52 that you put there. So that is going to be 16 bits. So it is 35, 19, 8 and 52 basically, right? And in case of function code, it does not exist for I type format, so that is not there. So that is not applicable in case of I type formats. Okay, so let's move forward. So the two components for load store instruction using memory address, a register whose contents are known and an offset. So offset, as I said, is stored in that 16 bits. So these are the two components of a load store type instructions. Loading is when we are loading from memory onto a register. Storing is when we want to store a particular value from the register onto the memory. So that's how the load store differs from each other. So what is an offset? It is written in terms of number of bytes. So, or it could be represented in terms of number of words. So 32 byte offset is written as 32 but stored as 8 because we have a capacity of storing 4 bytes in the location as per the MIPS alignment restriction rule. Okay, so when we have an offset 8 is actually or when we have an offset of 32, it actually means that we have 8 different locations where we can traverse it through, right? So imagine that somewhere you have an instruction LW equals to $T0, 1200, T1. So the memory location will be 300 basically, array 300th, because every location is able to store 4 bytes, right? So that's the reason when we have 1200 it becomes the memory location 300. So that 1200 becomes the offset. So we write it as 32 but we stored it as 8. That's what I'm trying to say here. The computation of the address is adding the content of the register with the offset, as we have done in the previous example, that we have added the content of the register which is storing the base address, and then we are adding that with the offset value. All registers has these components, and register 0 is used when no register is needed to be used. That is, register 0 is always storing the value of 0, right? Okay, so to summarize here, what we are trying to say is that the content of the register is storing the base of the array, memory array or memory location, that is added with the offset to get the effective address. From that address we will actually load the value onto the register, because that address is the effective address, is the address of the memory, okay, from where we need to make the transfer. Okay, now let me give you more exhaustive list of instructions that we usually very often use in MIPS. So these all are 3 operand instruction, as you can see. So the first is category number 1, which is arithmetic type, and in the arithmetic type we have add $T0, $T1, $T2, which means we are adding $T1 with $T2 and storing into $T0. Sub, which is differing or different, making a difference between $T1 content and $T2 content and storing into $T0. Then we have ADDI, which is add immediate, that is adding the contents of $T1 with 100, which is 100 is a constant, and storing the value into $T0. So the content of $T1 is added with 100 and that is stored into $T0. Mul is multiplying the content of $T1 with $T2 and storing into $T0. Division is dividing the content of $T1 and $T2 and storing into $T0. So these 5 instructions that you see are very popularly used in arithmetic type MIPS 32-bit processors. There are another 5 that are part of logical based ANDing. We can AND the content of $T1 and $T2 and store it into $T0. We can OR content of $T1 and $T2 and store it into $T0. So the first is called logical AND, second is called logical OR. We can also do a shift logical left or shift left logical SLL, which is shifting the content of T1 by the amount specified in $T2 and storing it into $T0, and the SRF is just doing shift right logical in a similar way. The third type is called register setting. What we can do, we can also move the content of $T1 to $T0 if we just want to interchange the content between registers, and we want to move the content of from this register to another register. We can just use this move operation. LI stands for load immediate. We can load up constant value directly into a particular register by using $T0, 100. 100 is just a constant value that we are using as an example. The next is data transfer. LW stands for load word. That means we are actually operating on a word. So now if you recall what I said in the previous lecture, the memory content will have the added value of the offset, which is 100, plus the content of $T1. So that becomes a location. From that memory location, the content is now loaded onto $T0. So we are loading 4 bytes because it's a load word. Okay. LB is load byte. So we are loading 1 byte in a similar way. So it becomes mem 100 plus $T1, and that is stored into $T0. Store word is just the opposite of load word. We are actually storing from memory back to the register. So it's memory 100 plus $T1, storing that content into $T0 from memory, or we actually rather storing from register back to the memory. So the content of T0, $T0 is stored back to memory 100 plus $T1. Okay. In case of load word, we were actually loading from memory to register. In case of store word, we are actually storing from register back to memory. So in the memory location where we want to store that is specified by 100 plus $T1, and that location becomes a memory location where we want to store that as. So that is again 4 bytes, and SB is again similarly doing store byte for 1 byte operations. Okay, now let's move to the next type, which is branching. In branching, we also have different types. So one is called BQ, $T0, $T1, and then we have a label where we want to shift the control to. So if $T0 and $T1 have same value, BEQ stands for branch on equal. So we will do the branching only if the content of T0 and T1 are equal. Then we'll go to label. BNE stands for branch on not equal. So if the content of $T0 and $T1 are not equal, then we go to the label. BG is branch on greater than equal. That is, if the content of $T0 is greater or equals to the $T1 content of register, then we'll go to the label. BGT stands for branch on greater than, which is if the content of $T0 is greater than the content of $T1, then we go to the label. BLE stands for branch on less than, which is if the content of $T0 is less or equals to the content of $T1, then we go to the label. BLT stands for branch on less than, that is if the value of $T0 is less than the value of $T1, then we go to the label. Okay, so BLE and BLT, they are similar. Only thing, one is branch on less than equals, second is only branch on less than. Okay, there is no equal condition here. The next type is set. So SLT, what it is doing, it is setting the value of $T0 to binary 1 if the content of $T1 is less than the content of $T2, else the content of $T0 becomes 0. SLTI is doing the same thing but now operates on a constant. So if the content of $T1 is less than 100, then $T0 is 1, else the content of $T0 is 0. And the last type is jumping category. What it does, we have 3 different types: J label, JR $array, and JUL label. So J label stands for go to label, will directly jump to the label. Okay, this is unconditional. We don't have any condition to check, we will always jump to a particular label. JR stands for go to address in $array. There is an address specified in $array. Array stands for return address. So we'll jump to that particular register, that's why it's JR, jump register to $array. JAL stands for jump and link. That means we will jump as well as we link it. So what it means, we will go to the label, but we know that the return address has to be PC plus 4. PC is keeping track of the current address. Okay, that is a pointer or a register that stores the current address. So we know that once we are done finishing the work at the label, we will have to come back to PC plus 4. So that's why we are linking it back to the main program from where we have actually made the jump. So it's jump and link. We jump, we finish, and then we link it back to whatever we want to come back to. So the coming back register address is stored in $array. So it is PC plus 4. Right? So as you could see here that we have so many different types of category, and all of these, of course this is not an exhaustive list, there are many more, but these are the ones which are prominently used in MIPS 32-bit processors to do various types of tasks and functions. Now coming almost to the end, you see the memory organization can be viewed as a large single dimensional array. I was referring to memory, so that is how it is. We basically could view it as a large single dimensional array with an address. A memory address is an index into the array, and if we perform byte addressing, which means the successive addresses are 1 byte apart. If you do word addressing, which is usually what it is for 32-bit MIPS, it is usually 4 bytes apart. That is why if we write 1200, it actually would be 300 if in terms of memory location, because 1200 by 4 bytes gives you 300. Okay, so if we write 32, it is actually stored as 8 because it's 4 byte apart. So that's how it is in case of MIPS. So in today's lecture you have seen several things. Okay, you've seen R type format, you've seen I type format, you've seen J type format. In R type format you have OP, RS, RT, RD, shamped function. Okay, function code selects a specific variant of the operation in the op field or opcode field. What you see in all of these things is that a good design demands good compromise. So compromise chosen by the MIPS designers is to keep all the instructions of the same length, because eventually the plan is to make a good design. We will see what that design is gradually when we enter into the courses, how the processor actually looks like, thereby requiring different kinds of instruction formats for different kinds of instructions, right? It is obvious, because you cannot just have one instruction format to do all kind of instructions. The above format that I just talked about, which is this opcode, RS, RT, RD, shamped function, they are called R type formats. The second time is I type formats, which is usually done for immediate, like load store. And then we have a jump format, which is called jump based instruction format, right? So you could see that there are different types of instruction formats. Another thing that you should note is that the opcode value also changes. If you do load word, it becomes 35. If you do store word, it becomes 43. However, there is no effect on function code because there is no function field in the I type format. But in case of R type format, the opcode value is 0 for both add and sub. That is why we need a differentiation to differentiate whether it is add or a sub by having a specific value specified in the function field, right? So that's why it is 32 for add and 34 for sub. That's how it basically operates upon. Now if I ask you what will be the instruction format for ADDI? Now ADDI will have instruction format as I type, similar to LW and SW. Although it is doing an arithmetic computation, but it is working on an immediate field. So for that immediate field, we need 16-bit constant value. So if ADDI is $S1, $S2, 100, then we know that we need to add the content of S2 with 100, which is the constant value, and stored it back into $S1, right? So therefore that 100, the value 100 has to be stored in that 16-bit field, right, which you actually add with S2 and then store it back to S1. So that's how it basically works, and you will have the value of opcode also specified there. The opcode value will be 8 in this case. So that is another part of the lecture where I'll also tell you what the opcodes are for different types of instructions. We'll also do that example, so that you know what the most important opcodes are for all popular instructions. Fine. And similarly we had a shamped, which is shift amount. The shift amount will be used when we want to do some shifting. So if we have SLL, okay, shift logical left, then we want to shift it. For example, let's take an instruction SLL $T2, $S0, 4. That means we are shifting the content of register S0 by 4 bits to the left, and whatever is the number that gets stored into $T2, right? So this will be an R type instruction, and the shamped amount will be 4. Function code will be 0, opcode will be 0. right? RS value will be 0 because it is S0, and RT will be 0 because this is the value that we are actually specifying for the register, which is going to be 16, which stands for register S0, $S0, and this RD is going to stand for $T2. So this $T2 is the destination register. Okay, so on and so forth. We have several examples that we can do, and that you should keep practicing to get more idea about how MIPS instruction basically works. Okay, so we will wrap up today's session, and then we'll again continue with MIPS instruction more. I'll give you more examples. We'll talk more in details about how the other instructions work, or how other instruction formats work, how to determine their addresses, how to convert it into machine code, so on and so forth. And once you do, then you can try out some examples pretty much by your own choice. Okay, thank you so much.